Good afternoon, everybody. Thank you for joining us today in our live webinar from Catagen, today we're going to demonstrate the unique emulated drive cycle capability on Catagen's Omega technology. In the room with us today, we've got Professor Roy Douglas, Dr. Matthew Elliott, and myself, Curtis Irwin. We're going to hopefully be able to discuss the customer data drive cycle emulation, Catagen's drive cycle without an engine, and then extending the after treatment characterization beyond light off testing. So a little bit of a background for anybody who hasn't had the opportunity to join us before. Who are Catagen? Catagen are after treatment testing and emissions specialists, and we help OEMs, fuel additive lubricant companies, catalyst manufacturers, and other engineering service providers meet their development requirements. And our unique Omega technology, a recirculating gas reactor, can replicate engine flow rates, temperatures, gas compositions, and poison rates for various kinds of engines, either gasoline, diesel, hybrid, or biofuels. And our process delivers accurate and reproducible outcomes for catalyst aging, catalyst performance measurement, and after treatment system poisoning. I'm now going to hand over to Dr. Matthew Elliott, who's going to give today's live webinar. Please also, if you have any questions throughout, feel free to drop them into the chat. If they come to a natural pause, we'll try and answer them then, or we'll answer some questions at the end. Enjoy.
Thanks very much, Curtis. So as Curtis said, I'll be taking the webinar today around our drive cycle emulation capabilities on the Omega test reactor. So to begin the presentation, I'll cover some background around drive cycle testing and how we realize this within Catagen. Then move into how we actually take the sort of an example profile and work that into a physically emulated cycle on the Omega reactor. Then do some evaluations of the test capabilities that we've had to date and showcase some repeatability and reproducibility that we have from that, before wrapping up with a few key salient points from our emulation process. So the next few slides are really some background. I actually touched on some of these during a previous webinar, so if you've seen these previously, I apologize, but I think it's necessary to set the background and context for the rest of the presentation. So starting off just with some information on drive cycle testing, I think for everyone on the call, it's probably reasonably clear that the drive cycle testing is really the true way to get a reflection of after treatment system and vehicle performance. So conventionally, this is realized through testing on a chassis dynamometer, which takes a lot of time and effort and cost to set up the vehicle on a rolling road and so on. So quite a lot of time and cost into testing on a vehicle. I think once we're on the vehicle, things are easy to progress with multiple drive cycles, but getting that set up, particularly during other development processes, can be quite difficult. Also, then the vehicle is needed to be there to support that testing. So in light of this, we at Catagen have developed our own technology to facilitate some drive cycle testing on our Omega reactor. So obviously that's an engine-free testing approach. And effectively we just have an example WLTC drive cycle here. So it's this drive cycle I'll be working through on some of the remaining slides, showcasing how we tuned that cycle for the Omega reactor and so on. So starting off, before we get into how the testing actually works, we need to think about how we actually start to begin testing on the Omega reactor. And so we have some Catagen developed AI, and this really underpins all of our drive cycle emulation activities. So this is sort of split into two key streams. The first stream is around retraining. So effectively, the artificial intelligence is able to learn from previous test data, and this then allows us to make projections out in terms of what we need to do for future testing. So this is really a case where we gather data on the Omega test reactor, process and store this data, and then we can use this to tune our digital twin of the Omega reactor. Then once we have a tuned digital twin, we can make predictions then. So whenever we think about predictions, the testing on the Omega reactor effectively receives a set of test inputs. We quite colloquially call this a test recipe. It's effectively a set of instructions that the reactor can follow to complete the test. So really the AI is there to support the predictions that generate those set of test parameters. So basically we feed in the test profile, and this then feeds into our AI, which is in the green square. And then effectively that spits out a set of test parameters. And then effectively how the AI fits into the sort of broader process. We have a flow diagram shown here, and this effectively shows step by step how we get from our target drive cycle to testing on Omega. So initially define the target drive cycle, like I've said, use the AI to convert this into a set of machine instructions, complete the testing on the Omega reactor, and then utilize the data that we've gathered on the Omega reactor to retrain the artificial intelligence and then improve the predictive accuracy of the AI and improve the quality of the target profiles. So effectively, this is an iterative process where we generate a new recipe, test that, and use the findings from that to support the generation of new and better recipes. So overall, from receiving a new target drive cycle to actually completing that test work is around a 24-hour period or really one working day for that. So over the next few slides, I will be outlining how we receive data and what that process sort of looks like for converting that into a drive cycle. So really, like I said, this is effectively an engine-free drive cycle, and the tuning and development process of that really focuses around matching our target temperature profile. So over the next couple of slides, like I mentioned at the beginning of the presentation, we're focusing around a WLTC test, but the technology is not limited just to WLTC. Effectively, any driving cycle that fits within our sort of testing parameters for the Omega reactor, whether that's NEDC, FTP75, even RDE type testing, we'll be able to support that. But the WLTC here is here as an example. So effectively on this image, we can see a black line, which shows our target profile, and then the light green line, hopefully you can see it, and that is our initial estimate from the AI. So that is physical test data with the first guess effectively from the AI. We can see, I guess in the next slide here, a little bit more detail. I think it's quite difficult to see over the full 30-minute window. But the initial predictions from the AI showed, I would say, pretty good agreement with the target profile there, considering that the data set that the predictions were made from is quite a limited data set. So effectively, took that test data, retrained the AI a couple more times. So in total, we've had 3 retraining iterations for this. And then we can see the tuned data in the dark green line where we're seeing much better agreement, particularly around cold start. Again, we do see, I would say qualitatively, a little bit more volatility in the measured, even the tuned data relative to the target. But for us, this is something that we could tune out further if we felt that it was necessary. But what we're going to show over the next few slides is that whilst we might have, let's say, a little bit of a mismatch between what the target and measured data is, it's able to show that we can have that data time and time again. And for us, that's really the key thing, that we have a repeatable and reproducible drive cycle, even if there is maybe a little bit of variation there relative to the target. Obviously, the more time we take to tune the test cycle, the more cost that adds, and the fact that we can get to a good approximation there within a short time window, I think is very encouraging for the testing protocol. So I mentioned during the previous slide that really repeatability and reproducibility for us is key. So if we think about the emulation, there's really 3 key factors that must be matched. So the emulation must match inlet temperature, flow rate, and our emissions concentrations. So effectively, the temperature of the gas going to the after-treatment system, the flow rate of gas, and then our hydrocarbon, oxygen, carbon monoxide, nitric oxide, CO2, water concentrations, and so on. They all must be matched in order to recreate that drive cycle. For this to be a useful process, we need to make sure we can have repeatability and reproducibility for the testing. So with this in mind, we want to be able to test a catalyst in, let's say, a morning in February, and then 9 months later, take maybe a different catalyst of the same specification and recreate that test and know for sure that the test is going to be equivalent to the original test, so that we can actually make proper comparisons between different geometries or between different systems. Or, for example, if we're going through an aging process, that any change in drive cycle behavior is actually from changes in catalyst performance rather than changes in the actual test cycle itself. So in order for us to evaluate and showcase repeatability, over the next few slides, I'll be comparing 3 different drive cycle tests. So on the screen at the minute, we have a plot at the top for inlet temperature, which is effectively similar to what we'd seen in the previous slide, and at the bottom, a plot for flow rate. So from the figures, the black line again is our target, and then we actually have 3 green plots in behind the black line. And I'd say, fortunately for us, it's actually difficult to discern the different test profiles in there, and this really is a testament to the repeatability of the test process. So, for example, at the top profile for inlet temperature, around the start of the test, we can maybe see a couple of different shades of green in there, and then towards the sort of end of the test, just before we finish at 30 minutes, again, see a couple of profiles. But effectively, throughout the entire duration of the test, we can't really differentiate, and there's no real discernible difference between each of the test profiles. And this is really, really key for us, because it means that we know that we can subject the catalyst to the same profile time and time again. And in fact, if we look at the average variation or the average range between the 3 tests across the drive cycle, across the 30-minute window, the average variance there between our test 1, test 2, and test 3 is less than 5 degrees C. Obviously then, the temperature and flow rate are 2 elements that we need to consider, but we also must consider our emissions. So for the sake of the presentation, so that we're not looking at slide after slide after slide of effectively very similar data, I've only showcased the carbon monoxide concentrations here, but we had similar agreement, and the trends were similar for both our hydrocarbons, NOx, and oxygen also. So in this slide, again, black traces are our target profiles, and then the 3 shades of green are our test profiles. As with temperature and flow rate, we see excellent agreement with the target and measured data. We do see some regions of an overshoot towards the sort of tail end of the test, where we have high CO concentrations during transient events, particularly as we're accelerating to high speeds. So I think for us, this is a point in which we can improve upon. And Roy, who's on the call today, we had some discussion this morning about how we're currently overcoming that challenge. So we have a solution that we're working on to improve that. Again, at the bottom trace, I've sort of highlighted a shorter window of the test to really showcase that repeatability. Again, there are 3 test profiles in there, although it might not seem like it. And again, we're getting this really great repeatability between tests. So it gives us good confidence that any results we get from the drive cycle testing are any variance we see in emissions performance is due to catalyst variance rather than test-to-test variance. So what does this then really mean for our catalyst performance metrics, and what does it mean for catalyst characterization? What can we take away from the actual testing? Because it's one thing to say that we subject a catalyst to a fixed set of inlet conditions, but if we can't actually take any useful output from that, then that test doesn't really add much value. So over the next few slides, I'm going to showcase how the catalyst actually performed across the 3 tests, and show that, again, we're seeing really excellent repeatability there. So on this slide, I have measured tailpipe emissions for CO, hydrocarbons, and NOx during the first 2 minutes of the drive cycle. So effectively during what could be classified as a cold start phase. So effectively, again, 3 test profiles shown here. For the carbon monoxide on the left-hand side, great agreement across the board there. And for hydrocarbons, we start to see a little bit of variation there, but I would say overall, again, excellent agreement between the 3 tests. And the same then could be said for NOx, maybe even a little bit more variation there. But again, I would say between the 3 tests, we can say that catalyst performed equivalently. And for us, we could then say, okay, throughout catalyst aging, we can do this evaluation, and we can see how is the cold start performance going to be affected as the catalyst degrades, or as the catalyst is poisoned, for example, or any other range of different things that we can do to the catalyst here at Catagen. Or we could look, for example, at 2 loadings where one catalyst is more heavily loaded towards the front, and understand what that means then for cold start emissions. So this is really something that we couldn't necessarily get out just from light off and OSC testing. It's the drive cycle testing capabilities that we have that can really support that additional insight to be gathered. Then looking again just at how the catalyst performance compared across tests, we have here CO conversion efficiency and NOx conversion efficiency. I have excluded the hydrocarbon conversion efficiency here because effectively all of the emissions happen in cold start, so there's not really much of interest beyond the first 2 minutes of the test. Again, similar story to what we had seen previously, where we effectively see three very closely matched profiles in terms of conversion efficiency throughout this 15-minute window. Again, showing this just to get a bit more granularity and allow a bit more insight to be gathered from the test data. I think it's quite difficult to show the lack of variation between test sample sets whenever we have a 30-minute test window, so the 15 minutes just allows us to get a little bit more insight. So for CO on the left-hand side, we effectively see excellent agreement there throughout, and we have those sustained periods where we have, let's say, less than 100% conversion efficiency, getting a good match there across all three tests. The NOx behavior is slightly different, where we have a series of effectively NOx breakthrough events, and they're very well aligned then between the three tests. So again, similar to what we've seen in the previous slide, where we have really good agreement between the different tests in terms of catalyst performance. The last area then that I looked at in terms of how the catalyst was performing was looking at cumulative emissions. So this actually tells maybe a little bit of a different story, and I'll touch on this over the next few slides. So effectively on the left-hand side, again, we have cumulative CO emissions. All figures here are normalized to the average cumulative emissions for each species, so CO average to average CO and so on. So effectively we see, again, pretty good agreement across the board for CO, with a couple of regions that I'll discuss in the next slide. Hydrocarbons, again, predominantly cold start related, and again, very good agreement there. And NOx, predominantly sort of during the transient phases at the end, where we had quite a lot of breakthrough NOx, and that's effectively where we're seeing most of the NOx coming during the test, but we're seeing excellent agreement there between the three different tests. This is kind of summarized then in the table that we have here. So what I've got is effectively our normalized cumulative emissions across each species for each test. So we effectively see for CO between tests, we're effectively within a 5% window of the average value, hydrocarbons within around 3 to 4%, and NOx within around 2 to 3%, well, really around 2%. So effectively, we do see, let's say, better prediction or capture of the NOx behavior than what we see in terms of the CO behavior. And I'll explain this on the next slide, but effectively, this can be linked to the breakthrough events that we can see. So during the first, let's say, 20 minutes of the test, we see excellent agreement between the NOx, or between the three different tests for CO. And then as we move into the sort of high-speed transient phases, there starts to become a little bit of variation there in terms of what our apparent cumulative CO emissions are. So I've pulled together a series of slides to try and investigate this, or a series of images to investigate this. So we've looked at this, and effectively the source of these, let's say, small differences in cumulative CO emissions are caused by small differences in measurements during our transient events. So if we actually look at the central plot, we see some variance in the engine out concentrations, particularly during the peaks. So a small peak here can then have a direct knock-on impact in terms of what our sort of tailpipe emissions are going to be. And so this kind of relates back to the point I had identified earlier in the presentation, where we feel that we could make some improvements, and we're actively working on those improvements and refinements for future testing. Again, looking at the bottom image, which we've already seen a similar plot to, we don't really see any discernible difference in CO conversion efficiency plot. So effectively between the three tests, there's very little difference to see between test 1, test 2, and test 3 in terms of CO conversion efficiency. But effectively, we can summarize the sort of what is causing our step changes in our CO cumulative emissions across the three tests as very small differences in measurement, but these are then amplified during transient conditions. So again, Roy and I have had some good discussions on this about how we can further improve the capability. I think we've taken many big steps towards reaching a sort of a final solution for the drive cycle testing, but we will have sort of small iterative improvements from here on out to sort of help improve that further and further, and just allow that test to become more refined and a little bit more mature. So I think just to summarize what we've covered so far, effectively we've seen that it takes quite a short period of time to tune a new driving cycle. then we've seen that that test cycle is repeatable, both in terms of what the inlet conditions to the catalyst are, and also in terms of what the performance metrics from that catalyst are. So effectively, we have a proven solution for drive cycle emulation on Omega. And we can then ask the question, what does this actually mean for after treatment development? So we have, like I said, this accurate, repeatable, and reproducible test, which allows us to have increased certainty for optimized powertrain development and calibration. So whenever I talk about increased certainty, if we imagine each element of that development process has some inherent uncertainty around that, if we can have improved certainty around catalyst performance, then that allows us to be less conservative with some design decisions, such as PGM loading or catalyst volume, many other different factors, and we can effectively have more certainty during this phase of the sort of catalyst or after treatment development process, and then that can pass on benefits throughout in terms of time saved, cost, and so on. On time saving and cost, this method itself is actually a very time and cost effective method of determining after treatment performance under drive cycle testing conditions. So, like I said, there's no requirement for mounting in a vehicle and testing in a chassis dynamometer. For the testing here, we effectively have the after treatment system mounted in the Omega reactor, which could take, let's say, around 1 hour. And then if we've tested before, we can have the drive cycle test complete within a subsequent hour, depending on the test. So effectively, it's a very, very time efficient method of completing the drive cycle testing. And because it's time effective, it can also be very cost effective. Another benefit that we see with this is the ability to support after treatment system development much earlier in the design process or development process, where we can develop the after treatment system alongside an engine or a vehicle, where we can take the case I've shown here is measured drive cycle data, but we can also handle simulated drive cycle data, which would allow us to evaluate the after treatment system on a driving cycle much earlier in the design process, where we don't rely on a donor vehicle or a donor engine to test on, and then that means we can get this really high quality, high value data much earlier in the process. Another point which I think is particularly interesting is that we've obviously designed the process to be repeatable and reproducible, but this has the benefit then that we can introduce controlled variation. So we can understand what, let's say, small changes in ECU calibration might have on drive cycle performance. We can understand effectively tweak or adjust some of the test parameters and understand what impact this has on drive cycle performance. So effectively, rather than having to actually make changes to an engine or a vehicle or an ECU calibration, we can understand, okay, if we make this small change, it may change condition X, and then we can understand what impact that has on after treatment system performance. And I think this is extremely valuable in that it effectively allows us to have a very flexible test bed upon which we can test, or we can introduce this controlled variation and complete a lot of test work very time efficiently. And then finally, I guess relevant to some of the current work that we're completing, the fact that we can drive cycle test on Omega now means that we can integrate that during after treatment system aging activities. So for example, OBD limit aging, where we're need to be quite cognizant of, I guess, very substantially aging the after treatment system, but still making sure it is emissions compliant. We can complete a lot of that, at least preliminary or sort of intermediate step drive cycle testing on the Omega reactor. So there's a lot less transfer to and fro of after treatment systems. We can age an after treatment system, complete a drive cycle test, other characterization tests, and then be aging again effectively the same day, if not the subsequent day, depending on when we actually start the test. So we kind of have a lot more flexibility in that regard in terms of being able to complete the drive cycle testing. And I think that adds a lot of value to those type of activities. Other areas where this could be useful for might be in PGM optimization, where we can effectively evaluate catalyst performance, not just in terms of let-off and OSC, but also in terms of drive cycle performance and how that changes throughout the course of after treatment system aging. So thank you very much for joining the webinar today and for listening to me presenting the slides. I think we'll now we'll just have a short Q&A, and I think Curtis, I'll hand over to you to handle some of the questions for that. So thank you very much.
Okay, great job. Thanks very much, Matthew. Very interesting presentation. If anybody does have any questions for us, please feel free to post them in the chat, and we'll work our way through them. I suppose I was just thinking a little bit, Matthew, during that too, was if we think about new legislations incoming and how this might help new OEMs or new vehicle developers prepare for the new legislations. I was thinking that this allows them to really develop their catalyst alongside the engine development. But really also for older models, there's the opportunity to quite easily re-homologate. So with the continuous change in prices that we're seeing for PGM, there's an opportunity to test, because we've already got all of the engine data, for example. We could test and show that the emissions to tailpipe are still well within legislative tolerances. So there's quite a range of flexibility there as well.
Yeah, I think so, Curtis. And I think on the upcoming legislation around, well, actually, Roy and I have had some discussions around how useful this may be for RDE, where we need to consider all potential operating cases for a vehicle, and the fact that we have that tool set at hand where we can look and emulate, let's say, 20 different drivers for a system, provided we have some indication of how each driver may impact on the engine out conditions. I think we have the ability there to recreate those test conditions on the Omega reactor and have high confidence that they are the correct values and that is a repeatable metric, and we can see then how driving aggression, for example, impacts tailpipe emissions or any sort of other number of factors. So I think, Roy, I don't know if you have anything to add to that, but I think there's a lot of potential value in that whenever we consider upcoming legislation.
Yes, well, the RDE new legislation coming in is going to impact severely on the cost of homologation, and we feel that we could at least do a high percentage of it on here, looking at the areas of the map that perhaps are a bit harder, particularly to test on road, and then confirming our results against on road. So we may be able to get to the point where there was, say, only 25% of the map needed testing on the road, and the rest could be run automatically on our system. But once we understood what the requirements of those were going to be.
Yeah. Okay, just a question to come in then. In the development cycle, when do you feel the right time to do the test is? I suppose we slightly touched on it there, saying that we can do it alongside the engine, but I don't know if as early as possible would probably be the right answer to that. I don't know, Matthew or Roy, if you have any more to add on that.
No, I do like the idea of the parallel development, because we know that this is a big limit for manufacturers, how long it takes to get new models out, and it's a very competitive world where everyone is trying to speed up this with a mix of simulations and new technologies, and I think we can help with both of those.
Yeah, just to add to that, I think it's useful in that it fits in across the entire development cycle, so we can be understanding, for instance, how different formulations early on in the development process might behave, or we can understand potentially how variations in calibration actually impact performance as well. So I think it fits in quite well across the board. So when is the right time to do the test, I guess? If anyone is interested in that, we could have some discussions and see how that fits in with your current development activities.
Yeah, the other one that could perhaps help with is warranty claims. So if a catalyst come back because of a light comes on early during the warranty period, we could easily run it and test it and try and get into it and understand where the problems have come from.
Yep, Okay, thank you. And another question, what do we see the benefits of this test? So being able to do the drive cycle test in the Omega reactor. What would benefits of the drive cycle over a light off an OSC be? Or I suppose just to slightly answer that or add to that question is, how does it add to the light off an OSC and our understanding of the catalyst performance?
Yeah, I can answer this, and then Roy, I'm sure you might have some things to add in afterwards. I think for me, the benefit is that it allows us to see, obviously, the light off an OSC or let's say reasonably static type test conditions where it gives us, let's say, a finite value that we can easily work from, and that's obviously very useful for comparing different specifications or comparing different catalyst loadings, for example. But it's not necessarily tangible in terms of what the catalyst performance is going to be. So whenever the vehicle's on the road, the light off, okay, we can understand how the light off might change, but what does that actually mean for tailpipe emissions performance? And at the end of the day, the after treatment system is there to control tailpipe emissions. It's not there to have a certain light off temperature. So I think it effectively allows a much more tangible metric whenever we're thinking about emissions compliance to be determined during the aging process, for example, or allows a much more tangible metric to be placed during PGM optimization type activities and so forth. And so I think that's where a lot of the additional benefit there over light off and OSC are. Now they're still critical parameters for catalyst development and understanding and quantifying catalyst behavior, but I think for transferring that into what we might expect vehicle behavior to be, I think that's really where the drive cycle testing is very useful and important.
Yeah, and I think perhaps the light off is very important for CO and hydrocarbons. And you can see, for example, that nearly all, 95% or something of the test emissions on hydrocarbons come from the light off period. But it's interesting to note that the CO and NOx in particular comes from later on once you've got light off. So in that case, the light off isn't going to be particularly helpful. We've been thinking for a long time how to evaluate post light off, because we do notice that in a heavily aged catalyst that you never reach 100% even after light off. And so we feel that this will be very helpful in assessing that. Also on the OSC, whenever you get heavily aged catalyst and the OSC has effectively gone to zero, then how do you further assess? Zero is zero. So we think that there is a lot of new aspects that can be investigated, and you could, for example, just take a section out of the drive cycle and look at that. You had commented, Matthew, that the NOx all comes from the heavy driving near the end of the cycle, and you could just look at that and investigate it for NOx and look at the impact of different catalysts in that part of the cycle, which is very difficult to do if you're trying to do it on full drive cycles on a car.
Yeah, I think, and just I think for the benefits of being able to do that on the Omega reactor is some of the things that I was thinking of was the flexibility that we have, and Matt has touched on it about the variability of changing the driver setup as such. So earlier we were able to quite easily see what the impact would be if we ran lean, and we can effectively run the test and have it analysed within 45 minutes, and be able to do that obviously with an engine and a test cell. Yeah, it can take significantly longer, and you've got to allow everything to cool down again before you can run the next test on these examples. So there's saving the time there as well. And then the other one is the availability, obviously, because the Omega reactors are designed specifically to test the after treatment systems, and they're readily available for the after treatment system, where the car or the vehicle may be booked previously for other development testing, and so you're just trying to wait for your time. So I think those are benefits that we're able to offer with the Omega reactor.
It's like having a very repeatable driver in the car, almost like the perfect driver, so that you can have exactly the same test the next time around. A few years ago, I was involved in a lot of fuel economy testing, and one of our biggest issues was we had 5 different professional drivers. Now, these were properly consummate professional drivers, and we were still seeing a variability of about 20% in fuel economy. So that's such a huge impact on this, and we can take that out because you might only be looking at a few percent improvement, and that means you always would have to have exactly the same driver, and they would have to be in exactly the same temperament during that particular day. So if you like, we can have the perfect robotic driver here.
Again, next questions come in is, what type of drive cycles can Catagen run, and are you limited, or are we limited to WLTC? So I think Matthew briefly mentioned earlier that really we can do FTP 75, RDE, if we wanted to look at any DC, but really with the way that the AI is set up and the digital twin, we're capable of replicating any input. So depending on the requirements. So we also didn't mention the WNTC, so for the motorcycle industry. So we're really not restricted there in what we're able to offer and to investigate.
Yeah, I think that covers it quite well, Curtis. Effectively, if we have a flow, a temperature, and exhaust gas composition profile, we can take that and try to recreate that in our Omega, and unless the temperatures are extremely high or the flow rates are extremely high, I think then that's effectively within our reach. So motorcycle, light duty automotive, even larger than that, we've quite a lot of infrastructure in there to support a very, very broad range of possible applications and possible driving cycles.
And I think the equipment's adaptable. So for example, if we ended up with requiring higher NOx, we change our mass flow controller to put higher NOx in.
Absolutely. So does the digital twin also predict tailpipe emissions?
So I can start this one off. Maybe Roy and Curtis, you can potentially add to what I'm answering. The digital twin that we have, if we consider the digital twin of the Omega, its primary function is to understand the behavior of the Omega reactor and how that effectively allows us to link what, in terms of a target profile, with a set of machine instructions for the Omega reactor. So the digital twin in that regard, our Mega digital twin in that regard, only really allows us to predict inlet emissions for the catalyst. But we do have the Catagen catalyst kinetic model, which effectively allows us to then predict what the tailpipe emissions may be from a test profile. And I think the really nice thing is that we have the Omega reactor, which now has the drive cycle capabilities to recreate that great repeatable and reproducible drive cycle data that we can actually use to feed into the kinetic model and allow those predictions to get better and better over time. So I think the physical emulation and the virtual simulation tool set actually go very, very well hand in hand. And I think we can effectively utilize one digital twin for allowing us to recreate drive cycles, and another digital twin in our Catagen catalyst kinetic model, which effectively is a digital twin of a different nature to predict the catalyst behavior and tailpipe emissions.
Yeah, well then, just going on to that catalyst kinetic model, we've already used it quite a few times as backup for ourselves and to help understanding whenever we're doing an aging profile, that we can take the light off data and then feed it into the model to see, are we close to what we're expecting the final tailpipe emissions to be. And interestingly, I think we're all quite excited with having this drive cycle capability, because we can look at that to investigate the accuracy of our model. the model has been mostly developed using fairly new catalysts, if you like, catalysts with good conversion efficiency. Now we have the ability to test on the reactor and get results for heavily aged catalysts and to test our model against those and to tune it a bit more. So I, for one, am quite excited to try that out.
Yeah, I think just the further sort of capabilities of that is we're also then going to be able to look at simulating aging through the kinetic model. So we'll have the tailpipe emissions, say, for example, 50,000 kilometers, the catalyst is aged, and we can replicate that through our drive cycle emulation, and then we could simulate what it would look like after another 50,000 kilometers through the kinetic model, or predict it after full useful life, for example. So I think the capabilities there are really not capped. It's the best way to describe it. And then another question then is, do I need to have real emissions data? So I think this is around the inputs that we require to be able to emulate a drive cycle. So I guess I'll let Matthew answer that one for us.
Yeah, I think from that point of view, the AI or the tool set that we have, it can differentiate whether that's actual real measured data or if it's simulated data for engine out conditions, which I think is quite useful in that. I guess this is where I've touched on a few times that the tool set and the Omega drive cycle testing can fit in much earlier in the drive cycle process or the development process, where we can take simulated data and we can evaluate how the after treatment system performs under those simulated conditions. And at that point, there might be simulated conditions for the engine, but they're real conditions and physically measured conditions for the after treatment system. And so we do have the flexibility there that we could take measured data or we could take simulated or predicted engine out data, and we could use that to evaluate the after treatment system performance.
Yeah, I think the other thing we can do is that we could take previously measured data and assess how applicable it would be to a new model, say, and match it up as best we can so that we can do after treatment testing well before you have a new engine in place. It's something that we're hoping that our new database will help us to look at. So as we gather up database information, I would hope to non-dimensionalize a lot of this data so that we could then say that one litre engine data from a particular vehicle could be recalibrated to produce 2 litre engine data on another vehicle. Of course, you can't use SI engines to predict, say, diesel engine performance, but we can match up for particular diesel engines. And as we build our database and we get more and more of this information, then our confidence level in that data, I think, will grow as well.
Yep, and just as in case there's any more questions come in, we'll hang on for another few minutes. But with regards to the poll, thank you to everyone who took part in that. Quite a spread across whether PGM optimization, what the priority is in your strategic roadmap. So I guess it really depends on the industry. So obviously if you're an OEM, you're going to want to try and have that as optimized as possible. But if you're not working directly with the catalyst, it's not having as big an impact on you. But it's interesting to see that it is obviously a consideration for some, and for others it's not a priority. But I think we briefly touched on how the drive cycle can help optimizing the PGM loading, which is obviously for those of interest, great news. Okay, I think we'll wrap it up then. Thanks again to everybody who was able to come online and join our live webinar. Thanks very much to Dr. Matthew Elliott and Professor Roy Douglas for the presentation and for the Q&A. And hopefully we'll be having another webinar in the new year, so everyone can keep keep an eye out, and look forward to speaking to you all again then. Great. Thank you.
Thanks all.
Thanks everyone. Goodbye.